It began with a question so quiet it almost felt like a whisper against the dark. What if the universe isn't what we think it is? And then came the machine, a gleaming, gold-eyed creation of human hands drifting a million miles from home, unfolding like a metal flower in the cold. The James Webb Space Telescope was just built to see deeper. It was built to see earlier into a time when nothing should have been old enough, massive enough, or bright enough to exist. Yet the moment it opened its mirrors to the void, the universe blinked back with impossible answers. Galaxies that shouldn't have formed. Stars too heavy for a newborn cosmos. Structures arranged with a maturity that defied the very timeline carved into physics. For a moment, the silence felt sacred, because how could something so young contain memories so ancient? How could order emerge before chaos had time to breathe? Just wrapped in its shield of darkness became more than a telescope. It became a mirror, not reflecting us, but reflecting a universe that refuses to obey its own rules. And as its images arrived, pixel by pixel, one truth lingered in the air like a held breath. The cosmos is hiding something. In the beginning, there were no galaxies, no stars, no light. There wasn't even darkness, because darkness needs space to stretch its wings. And there was no space yet. There was only a trembling moment so small, so dense, so indescribably compressed that even calling it a moment feels like an exaggeration. Physicists call it the Planck era, a span of time so brief that if you divided 1 second into 100 trillion pieces, you'd still be nowhere close. In that impossible sliver, all the laws of nature fought to exist. Gravity tried to define itself. Time tried to take its first step. Space tried to draw its first line. And out of that struggle came the earliest rule of reality. The universe must start simple. For decades, this rule was questioned. How could it be? Complexity takes time. Order needs patience. Stars require thousands of degrees and millions of years to ignite. Galaxies, vast cities of suns, need hundreds of millions of years to gather, spin, and sculpt themselves into spirals or spheres. The first rule felt natural, comforting even. Like the universe was following the same logic everything else follows. Infancy before adulthood, seeds before forests, sparks before flames. We believed this rule not because we had seen the beginning, but because everything we had seen suggested it must be true. After the Planck era flickered into existence and vanished, inflation took the stage, a burst so violent, so impossibly fast, that the universe expanded from smaller than a proton to the size of a grapefruit in a breath. This wasn't a gentle growth, it was an eruption. Space stretched faster than light, smoothing out any wrinkles, erasing any ancient scars, resetting the cosmic canvas. Inflation was nature's reset button, wiping away complexity and leaving behind a universe that was uniform, predictable, and astonishingly simple. No stars, no galaxies, just a hot, dense ocean of energy waiting to cool. Then came the first particle quarks swirling into protons, electrons buzzing freely like fireflies in a furnace. For hundreds of thousands of years, the universe glowed with a brightness so intense that atoms couldn't hold together. Light couldn't travel. Photons were trapped, bouncing endlessly between particles. It was a universe of pure chaos and blazing pressure. But even then, the rule still held. Nothing complex, nothing heavy, nothing ancient could form. Not yet. As the universe expanded, it cooled. And as it cooled, the chaos softened. Around 380,000 years after the beginning, everything changed in a single cosmic sigh. Electrons slowed just enough to be captured by protons. Atoms appeared small, simple, fragile, and for the first time, light became free. This was recombination. The moment the universe became transparent, the moment photons could finally travel unhindered. Today, we see that ancient light as the cosmic microwave background, a faint glow left over from a time when everything was still impossibly young. And after that moment of clarity came the longest silence the universe has ever known. The cosmic dark ages. No stars, no galaxies, no explosions, no illumination. Just a vast expanding emptiness filled with cold hydrogen, drifting without purpose. If you could stand there, though nothing existed to stand on, you would see nothing in every direction. Only the promise of future light. Only the patience of a universe that seemed in no hurry to wake up. According to the rules we carved into the textbooks, those dark ages would last hundreds of millions of years. Only then, slowly, shyly, would the first stars flicker into being. They would be massive, but not impossibly so. They would burn quickly, but not unbelievably. They would begin as scattered islands of fire in an endless night, too far apart and too short-lived to gather into galaxies immediately. Structure, we said, needs time to become majestic. By 100 million years, the universe should still be dim. By 200 million, the first primitive galaxies should be forming small, irregular, fragile. By 300 to 400 million, we should begin to see the earliest hints of large-scale structure. Cosmic webs, clusters, small spirals taking their first uncertain shapes. The universe had rules, and we trusted those rules, not because we are arrogant, but because we are human. We look for patterns so we can breathe. We build expectations so we can understand. We believe beginnings must be simple because our beginnings are simple. A child does not arrive speaking poetry. A seed does not sprout as a forest. A spark does not begin as a star. So we assume the cosmos followed the same story. Simple first, complex later, chaos first, order later, darkness first, light later, and for decades every observation seemed to agree. Every telescope told the same story. Hubble peered back billions of years, and even then, at the edge of visibility, it found galaxies that looked primitive, small, and unfinished. Nothing contradicted the rule. Nothing challenged the timeline. But then we built something new. A telescope colder than space itself. A mirror polished with atomic precision. A machine capable of catching the faintest whispers of the earliest stars, stretched into infrared wavelengths by the expansion of the universe. JWST. It was just another tool. It was the first human-made eye capable of seeing the universe not as it appears today, but as it was when it was still learning to exist. And as it drifted to Lagrange point 2, unfolding its golden mirrors like petals opening to the dawn, we prepared ourselves for confirmation, not rebellion. We expected to see tiny galaxies, dim stars, slow beginnings, the cosmic childhood we had always imagined. But the universe had other plans. The first images arrived quietly. No explosion, no drama. Just data, a tiny patch of sky magnified into a cathedral of ancient light. And tucked within it were shapes distant, red-shifted, older than anything we had ever seen. We measured them once, twice, a dozen times. Their light had traveled more than 13 billion years, but the galaxies themselves, they weren't tiny. They weren't primitive. They weren't shy sparks in the dark. They were massive dens. even hundreds of billions of solar masses. They were mature shaped, organized, rotating with impossible grace. They were bright, too bright for stars that should barely have existed. According to everything we knew, these galaxies should have taken billions of years to form. And yet there they were, shining at us from a time when the universe was only two of its current age. This was the first crack in the first rule. The universe must start simple. But these galaxies were not simple at all. We dug deeper, we zoomed in, and the contradictions multiplied. We found black holes, not small ones, not fresh ones, but monsters, millions or even billions of times the mass of the Sun, sitting right at the cosmic dawn. Black holes so heavy, they should have required entire epochs to grow, and yet they appeared fully formed, like characters walking onto a stage, already knowing the lines of a play that had not been written yet. We saw structures aligned in ways that should have taken eons to sculpt. We saw star clusters burning hotter and brighter than theory allowed. We saw galaxies too smooth, too ordered, too evolved for a universe still supposed to be in its infancy. It was like opening a baby photo and seeing an adult staring back. Something was wrong, or something was hidden, or something was missing from our understanding of how beginnings truly unfold. For a moment, we doubted our measurements. Then we doubted our models. Then we doubted the rule itself. Because if the universe does not start simple, if complexity was there from the beginning, if order arrived before chaos had time to breathe, then everything we thought we knew about the first billion years is open to question. Maybe inflation didn't smooth everything perfectly. Maybe matter clumped faster than we imagined. Maybe dark matter behaved strangely in those early moments. Or maybe, and this is the possibility that keeps cosmologists awake, maybe the universe's timeline is not as straightforward as the equations suggest. JWST wasn't trying to break the rules. It was simply revealing what the rules have been hiding. And as the data poured in, one truth became undeniable. The universe we expected is not the universe we got. The first rule, the comforting rule, the rule that said beginnings must be small, early structures must be weak, and nothing massive should exist. Near the dawn was beginning to crumble. The universe was whispering something we were never prepared to hear. And as JWST looked deeper, far past the darkness we once mistook for emptiness, something remarkable happened, something we could no longer ignore. The rule wasn't just bending, it was breaking. At first, the anomalies came quietly, almost politely, like faint ripples at the edge of a still lake. Astronomers stared at the early JWST datasets, expecting the usual. Dim smudges, small blotches of infant galaxies barely bright enough to register. And yes, at a glance, that's exactly what they saw. Little red dots scattered across the deep field. Nothing unusual, nothing shocking, nothing that would rewrite the story of creation. But when the numbers were decoded, when those faint dots were translated into distances, ages, and masses, something extraordinary emerged from the pixels. Galaxies at redshift 12, then 13, then 14. Galaxies so far away their light began its journey when the universe was barely 300 million years old. Galaxies so ancient we are seeing them before the Milky Way even dreamed of existing. Yet these weren't tiny cosmic embryos. They weren't timid sparks in the dark. They were giants, fully grown, older than they had any right to be. The shock began with a galaxy labeled simply Glass Z12. It looked ordinary, a faint smear of light, But when its redshift was calculated, astronomers froze. This object existed only about 350 million years after the Big Bang. According to everything we know, a galaxy at that time should be small, rough, disorganized, barely held together. Yet glass Z12 wasn't weak at all. It shone with confidence. It had already formed millions of stars. Its structure suggested something closer to adolescence than infancy. It was the kind of formation cosmologists expected to see billions of years later, not mere moments after the cosmic beginning. But glass Z12 was only the first whisper. The universe had much louder secrets to reveal. Next came glass Z13, showing up at around 320 million years after the Big Bang. And then Sears 1749, a galaxy that may sit at redshift 17, placing it just 230 million years after the beginning. If this number holds, it means that in less than the blink of a cosmic eye, the universe had already assembled structures that defy every chart, every timeline, every model. It is like discovering entire cities built during the age you thought humans were still learning to walk. Every new red dot felt like a contradiction. Every deeper image felt like a confession. But the real shock wasn't it just their age, it was their mass. Galaxies this young should contain at most a few million stars. JWST found galaxies with billions of solar masses, some with 10 billion, even 100 billion suns worth of material. These were not cosmic seedlings. They were full-grown forests, flourishing long before the soil had time to exist. How do you build something so heavy so quickly? How do stars form in such numbers in such a short span? How does gravity sculpt a masterpiece when it hasn't even warmed up? And yet there they were, bright, bold, and unapologetically massive. It was just the mass. It was the brightness. These early galaxies weren't to faint memories barely clinging to the edge of observability. They were loud, radiant, burning with a ferocity that shouldn't have been possible in the cosmic dawn. Their luminosity suggested star factories operating at impossible speeds, churning out new suns like sparks from a grinding wheel. Some galaxies glowed so brightly that they outshone entire mature galaxies in the nearby universe. How can something so young shine like something so old? And then, the strangest twist of all, structure. At these early times, galaxies are supposed to look chaotic clumps, irregular shapes, messy distributions of stars thrown together randomly. But JWST detected spiraling patterns, smooth disks, structures so well organized they seemed sculpted by ages of gravitational dance. A spiral galaxy, a spiral appearing when the universe was still in cosmic infancy. Spirals are delicate. They need time. They need billions of years of rotation, settling, and gravitational interactions to unfurl their elegant arms. Yet, JWST showed that some had already begun this dance within the first few 100 million years. It was as if the universe skipped childhood entirely. Even more unsettling were the heavy elements detected in some of these galaxies. Heavy elements, carbon, oxygen, nitrogen, even hints of iron, are created in the hearts of stars and thrown into space when those stars explode. But this process takes time. Generations of stars must be born, burn, die, and scatter their ashes. So why were these ancient galaxies already glittering with heavy elements? Why did their light carry signatures of chemical maturity? If heavy elements were already present, it means earlier stars had already lived and died long before such cycles should have been possible. The timeline was collapsing in on itself. Something was off. The universe shouldn't have had this much complexity so early. According to the Standard Model, the first stars were massive, short-lived metal-free giants known as population 3 stars. They should have taken time to appear, and even more time to explode and seed the cosmos with heavier elements. Yet JWST found galaxies where this cycle seemed already well underway. It was like discovering a civilization where the ruins are older than the people who supposedly built them. As the data grew, the anomalies multiplied. Sears 1019, a galaxy just 570 million years old, harbored a black hole 9 million times the mass of the Sun, a monster that should have required nearly a billion years to grow. And that was just a warm-up. More candidates emerged. Black holes too big, too early, too hungry. Structures that simply should not exist under our current understanding of cosmic evolution. Everywhere JWST looked, the universe's early timeline was being torn apart. Astronomers tried to explain the numbers away. Perhaps the distances were wrong. Perhaps the redshifts were misread. Perhaps the galaxies weren't as massive as they appeared. But each reanalysis only deepened the anomaly. The light was real. The distances were real. The masses were real. The brightness was real. The universe was confessing something, and it wasn't subtle. Why is the early universe filled with enormous galaxies? Why are there supermassive black holes sitting calmly at the dawn, as if they had always been there? Why does the cosmos seem to build faster, brighter, bigger than physics allows? Some researchers suggested these early galaxies must be extremely efficient at forming stars, far more efficient than modern galaxies. But efficiency has limits, and the observed numbers pushed far beyond those limits. Others suggested exotic physics, modified dark matter models, faster collapse rates, new cooling mechanisms, but every explanation seemed like a patch rather than a revelation. Maybe the universe was simply more eager than we imagined. Maybe creation rushed its earliest steps, sprinting before it learned to crawl. Maybe the cosmos was the slow painter, but a frantic one, splashing entire masterpieces across the canvas while its colors were still drying. As the anomalies piled up, a quiet question began whispering through the halls of cosmology. Is the universe older than its clock? If these galaxies truly existed just 300 million years after the beginning, and if they genuinely possess the mass, structure, and chemical maturity JWST suggests, then perhaps our measurement of cosmic time itself needs rethinking. Maybe inflation lasted differently. Maybe expansion unfolded in ways we haven't yet understood. Maybe the universe began with seeds of complexity already embedded in its fabric. Or maybe, and this is the possibility that feels like stepping off a cliff, maybe the early universe wasn't empty. Maybe it inherited something, patterns, structures, clumps of matter that survived something before the Big Bang. No one knows. But the questions keep coming. Why did galaxies mature before their time? Why does the cosmic dawn look like a twilight of previous worlds? Why does the universe behave like it remembers something we do not? And then, as if the universe wanted to twist the knife a little deeper, JWST revealed the JWST Z130 galaxy, one of the brightest, most massive early galaxies ever observed. Its star formation rate alone seemed impossible, as if the galaxy were forging suns in a frenzy, building a cosmic city overnight. And wrapped around it were hints of rotation, organized motion, a gravitational choreography that should have taken billions of years to develop. Every discovery felt like a plot twist. Every new object felt like a challenge. Gustav was just showing early galaxies. It was showing fully formed universes, hiding inside the universe's childhood. It wasn't just unexpected, it was uncomfortable. A universe that builds too fast is a universe that cannot be fully trusted. And yet it was beautiful, because these anomalies weren't mistakes. They weren't glitches. They were reminders. Reminders that the cosmos is not obligated to behave the way we want. Reminders that nature does not read our books. Reminders that the universe has always been stranger, faster, older, and more ambitious than our imagination. The deeper JWST looked, the more contradictions emerged. Young galaxies that look ancient, ancient light that behaves like it has lived many lives, a cosmos that should be crawling, but is already running. Each anomaly felt like a revelation, a cosmic wink hinting at hidden rules, forgotten histories, and beginnings written in languages we have yet to decipher. These early giants were not supposed to exist, but they do, and their presence forces us into a quiet, trembling disbelief. Because if the universe began simple, then where did all this complexity come from? If time is young, why does the cosmos wear the face of age? As JWST continued its silent vigil, the galaxies remained there on the screen, impossible, unyielding, defiant. And for the first time in a long time, humans had nothing to say, only to stare, only to wonder, only to let the silence hold the truth. They began as whispers, feigned distortions buried inside the early JWST data. Nothing dramatic, nothing that shouted its presence. Just tiny gravitational signatures, slight excesses of brightness, subtle hints of something dense lurking in the heart of galaxies far too young to hold such monsters. But as astronomers peeled back the layers of light, cleaned the noise, and traced the shapes of those signals, the whispers turned into a revelation so unsettling it bordered on impossible. In the earliest epochs of the universe, long before, stars should have had time to live and die. Long before galaxies should have matured, gravity itself had already collapsed into giants. Black holes, not small ones, not fresh ones, but massive ones, ancient ones, millions, even billions of times the mass of the sun. How do you build a cosmic monster before the cosmos itself has learned to crawl? The question struck like thunder through astrophysics. Black holes are supposed to grow slowly. Stars collapse into tiny seeds a few times the mass of the sun, and then spend billions of years swallowing gas, dust, and starlight, stretching their horizons inch by inch. There are limits to how fast they can grow. Physical limits. The Eddington limit, a threshold that says if a black hole tries to feed too quickly, the radiation it produces pushes matter away, slowing its growth. Its nature a speed limit on cosmic appetite. A black hole cannot simply gorge itself into greatness. And yet somehow, the universe produced giants at impossible speeds. JWST revealed objects like Sears 1019, sitting just 570 million years after the Big Bang, hosting a black hole 9 million times the mass of our Sun. Then came others some 100 million years older, some older still, each one a contradiction, wrapped in darkness. They existed before they were allowed to exist. Their presence cut straight through every model, every simulation, every assumption we had about how quickly gravity can sculpt something so immense. These black holes were not patient. They were not slow. They were born ancient. In a universe still glowing with the heat of its creation, in a cosmos still stitching its first galaxies together. The deepest wells of gravity had already opened their mouths, as if the universe wanted to anchor itself early, as if it needed weight, enormous, crushing weight, to stabilize its newborn structure. But why? Why would creation rush its darkest children? To answer that, we first have to understand how black holes should form. The standard picture begins with stars, the first generation, known as population 3, massive metal-free stars made entirely of hydrogen and helium, burning fiercely and dying quickly. When they collapse, they leave behind black hole seeds, perhaps 100 times the mass of the Sun. Those seeds then grow through accretion and mergers. But even with the most generous assumptions, even if they fed constantly at the Eddington limit, it would still take hundreds of millions of years to reach 1 million solar masses, and billions of years to reach 1 billion. The math is unforgiving. It says, this cannot happen in time. But the universe did not follow the math. So theorists offered new possibilities, each one stranger, darker, or more profound than the last. The first idea was simple and bold: direct collapse black holes. Instead of forming from stars, these black holes might have formed directly from vast clouds of primordial gas that collapsed under their own weight before stars could ignite. A shortcut, a loophole. Instead of a seed weighing 100 suns, the universe might have started with seeds 100,000 suns in size. But even that raised questions. How does gas collapse so quickly without fragmenting into stars? What conditions would allow such a thing? Direct collapse black holes require a delicate balance, too much turbulence. They split into stars. Too much cooling, they break apart. Too little cooling, they resist collapse. It's like threading a cosmic needle. Perhaps the early universe was good at threading needles, or perhaps something else was guiding the stitch. Another idea emerged: dark matter halos. Dark matter, invisible, silent, but heavy, could have created gravitational wells deep enough to accelerate the collapse of gas clouds. If dark matter clumped earlier than expected, it might have created cosmic traps where matter fell inward too quickly for stars to form, collapsing directly into black holes. But this theory simply pushed the mystery back one step. Why would dark matter clump so early? Why would it gather in halos dense enough to sculpt giants so soon after the birth of time? Then came the most radical possibility: primordial black holes. Black holes not formed from stars or gas, but from fluctuations in the fabric of space during the earliest instants after the Big Bang, from density spikes during inflation that collapsed under their own gravity. According to this idea, black holes could have been born within the first second of the universe, not slowly, not later, but immediately. Babies born ancient, mass without ancestry. If true, the universe's first children were not stars. They were singularities. Primordial black holes could explain the impossible masses. They could serve as seeds for galaxy formation. They could even make up a fraction of dark matter. But the idea carries a haunting implication. What we call the beginning may not have been as smooth, clean, or uniform as inflation theory suggests. If primordial black holes exist, then the earliest moments of the universe were chaotic, jagged, scarred by gravitational collapse before atoms even existed. A universe born already bending under its own gravity. Still, for all these explanations, direct collapse, dark matter halos, primordial formation, each one carries a deeper mystery as if the universe refuses to give a straight answer. Why did the cosmos prioritize black holes? Why introduce gravity wells before stars? Why plant anchors before building the galaxy walls that rely on them? Why populate the cosmic dawn with objects that seem to know they belong at the end of time, not the beginning? It is as if the universe began with conclusions instead of premises. As JWST pushed deeper, the contradictions deepened. Some early galaxies showed signs of active galactic nuclei, black holes swallowing matter so voraciously that their emissions outshined entire galaxies. These should not exist in a young universe. The processes required to ignite them should take ages. Yet there they were, glowing like cosmic furnaces, as if the universe wanted to start with the climax. The closer we looked, the stranger it became. Some galaxies were simultaneously too young and too old, their stars showing signs of heavy elements, their centers harboring large black holes, and yet their positions placing them so close to the beginning that they should not have had any time at all to undergo such evolution. It was like discovering a newborn with memories. Every explanation we offered created another question. If black holes form too quickly, why? If they grew too fast, how? If they were born too massive, from what? The deeper we reached into the cosmic dawn, the more the universe pulled away, offering shadows where answers should be. Some physicists began whispering ideas that once felt too speculative to entertain seriously. What if accretion limits didn't apply in the early universe? What if matter behaved differently at extreme densities? What if physics itself changed during the first few 100 million years? A universe with evolving rules, a cosmos that begins with different laws and slowly settles into the ones we observe today. Others proposed exotic scenarios, ultralight particles that cooled gas clouds rapidly, black holes merging in dense clusters far faster than expected, or dark matter interacting with normal matter in ways we have never observed. But each new idea, while imaginative, carried the same unsettling implication that our understanding of the early universe is incomplete, that the story of creation we have been telling ourselves is missing chapters, missing characters, missing the architecture that makes sense of these impossible giants. Then there is the most philosophical possibility of all, that time in the early universe simply does not behave the way we assume. Perhaps cosmic time flowed differently during the earliest epochs. Perhaps expansion, gravity, and the passage of time were entangled in ways that give us illusions of maturity in structures that should be young. A universe where the clock lies. As the possibilities multiplied, so did the discomfort. Because every theory, every model, every attempt to reconcile the early black holes with the expected timeline reveals something deeper about our limitations. We do not understand gravity as well as we think. We do not understand the early universe as clearly as we claim. And we may not fully grasp the relationship between matter, time, and the structure of existence. The black holes JWST found are not just scientific anomalies. They are philosophical fractures. They expose the cracks in our belief that complexity must follow simplicity, that giants must grow from seeds, that time must behave in ways familiar to our senses. These black holes behave like exceptions to the universe rules, unless, quietly, they are the rules, the ones we never realized we needed. Imagine a universe that begins in a rush, not a crawl. A universe that doesn't wait for stars to form naturally, but instead collapses entire regions of space into gravity wells capable of sculpting the cosmos. A universe that chooses to begin with anchors because it knows it must hold itself together. It sounds strange, it sounds poetic, it sounds unscientific, and yet the data remains. Black holes too big, black holes too early, black holes too fast, silent engines in the dark that should not be there and yet refuse to vanish. Perhaps the universe is not a story of gradual evolution. Perhaps it is a story of sudden decisions, of structure emerging under pressure, of gravity acting with purpose long before it should have known what purpose was. With each new observation, JWST turns the mystery deeper, sharper, more uncomfortable, because these black holes don't just defy our expectations. They defy our sense of order, our sense of time, our belief that we understand how the universe builds itself. They stand at the edge of logic like silent questions. And the more we try to answer them, the more the questions multiply, spiraling outward like galaxies born too early, too bright, too fast. In the end, we are left with a tension that refuses to fade, a sense that the blueprint of the universe may not be what we think, that creation may not follow the sequence we assumed, that the cosmos, in its earliest breath, may have written rules we have yet to decipher, and standing in the glow of these impossible giants, we can only listen to the silence they leave behind. In the earliest days of the universe, everything should have been simple, pure, primal. A cosmos made of only two ingredients, hydrogen and helium, drifting through an expanding darkness that had barely cooled from its own birth. No metals, no dust, no complexity. The universe was a newborn, made from the lightest elements, with no memory of heavier atoms. Iron was impossible. Carbon was impossible. Oxygen was impossible. These elements require time, long, patient time, the kind carved by star cycles. Birth, burn, collapse, explosion. Multiple generations of stellar death are needed to enrich the cosmos with anything heavier than helium. The early universe should have had no such history. No explosions, no ashes, no alchemy. And yet JWST opened its golden eye and saw something the universe should not have been able to show. Ancient stars infused with heavy elements, galaxies in the cosmic dawn glittering with metals, dust made of carbon, iron, and silicon swirling through regions that should have been untouched by any kind of stellar legacy. It was like walking into a freshly constructed home and finding ancient artifacts woven into the walls, like discovering fossils inside a newborn. The contradiction was immediate. Heavy elements before the universe had time to forge them. Metals without ancestors, dust without death. At first, astronomers doubted their own readings. How could a galaxy at redshift 13, a system appearing only 300 million years after the Big Bang, contain mature elements that require repeated cycles of star formation? How could complex dust appear in a universe that had hardly formed its first stars, let alone watched them die violent deaths? But the signatures were unmistakable. The chemical fingerprints were real. Carbon lines, oxygen emissions, iron traces, silicates, all whispering of histories that the universe had no time to live. It was as though time had folded, compressing epochs of stellar evolution into the opening pages of creation. In the standard story, the first stars, the mythical population three giants, were enormous, unstable, pristine. They lived fast and died in spectacular explosions, scattering the first heavy elements into space. But those stars would need to form first. They would need to burn. They would need to explode. And their remnants would need to gather into new systems. Only then could heavy elements begin to circulate. This process should take hundreds of millions of years. Yet JWST showed us galaxies enriched within a cosmic instant. Stars forming out of gas, already carrying the fingerprints of previous generations. Dust grains forged in furnaces that had no time to ignite. It was like the universe skipped its childhood and leapt directly into adulthood. The paradox deepened with every new image. Some galaxies revealed oxygen levels comparable to much later eras. Others showed carbon dust so thick it absorbed starlight like smoke. In one infant galaxy, astronomers found evidence of iron, one of the slowest elements to appear in the cosmic timeline. Iron requires not just supernovae, but type Ia supernovae, the explosions of long-lived low-mass stars. Those stars need billions of years to form, age, and explode. And yet there was iron glinting in the cosmic dawn, mocking everything we believed about the arrow of time. How does iron appear before stars have time to grow old? How does carbon appear before supernovae have time to breathe out their ashes? How does dust appear before the universe has warmed itself enough to generate the cycles needed to create it? Suddenly, the early cosmos did not look like a simple garden of hydrogen. It looked like a cathedral built from recycled stars even before the first stars should have lived. The theories began to shift and stretch in strange directions. Some suggested the first stars must have lived faster than expected. Monstrous giants burning through their fuel in 1 million years instead of 10 million. But even if they exploded at maximum speed, the timeline still wouldn't line up. The enrichment was too high, the dust too concentrated, the complexity too advanced. Others argued for hypernova explosions so violent they release heavy elements in massive quantities. But hypernovae alone cannot explain the widespread metallicity, the layering of elements, the chemical diversity found across early galaxies. Some proposed that the first stars weren't stars at all. Perhaps they were enormous, exotic objects, quasi-stars, powered by internal black holes whose violent growth triggered explosive outflows rich with heavy elements. Quasi-stars could live briefly, burn furiously, and enrich their surroundings quickly. But these are theoretical creatures, fragile in their existence, requiring precise conditions. Could the early universe really have been filled with them? And if so, why? The puzzle stretched further. JWST observed dust grains that seemed too large for early cosmic conditions. Dust does not simply appear. It forms from the cool remains of dying stars. It requires cycles of heating and cooling, shattering and clustering, pressure and time. Yet the early universe seemed to be carpeted with dust thick enough to obscure starlight, dense enough to shape early galaxy formation. Where did the dust come from? What stars created it? What history wrote it into existence before existence itself had a chance to unfold? The more scientists looked, the stranger the answers became. Maybe the early universe favored complexity over simplicity. Maybe, instead of crawling through its chemical evolution, it sprinted. Maybe it formed massive stars so quickly and so densely that the first enrichment cycle happened in mere moments. This would require star factories operating at near impossible efficiencies. churning out massive stars in such numbers that explosions became the earliest weather pattern of the cosmos. Or maybe the early universe wasn't uniform at all. Perhaps it began with fluctuations, pockets of density so extreme that stars formed instantly, burned violently, and seeded the surrounding space with the ashes of elements before the larger universe even noticed. These would be cosmic furnaces, microcosms of accelerated evolution, hidden inside the first 100 million years. Another idea leaned toward the philosophical. What if the universe is biased toward complexity? What if creation is not slow, but impatient? What if the cosmos is not a cold machine, but a force that rushes toward structure, toward chemistry, toward life-enabling ingredients, long before the equations say it should? It is a dangerous idea, yet JWST's images seem to breathe it. Everywhere it looks, complexity blooms too early, too bright, too heavy, too enriched, too soon. Dust clouds swirl like old memories in a universe that should have had none. Star nurseries glow with metals that should not have existed. Ancient galaxies appear with layers of chemical history written into their spectra, despite having lived for only a fraction of the time required to produce those signatures. It is as though creation itself refuses to follow the rulebook. And behind every scientific explanation lies an existential question. Why does the universe rush? Why does it forge complexity where simplicity should reign? Why does it compress eons of chemical evolution into the first breaths of time? Why is the cosmic dawn filled with echoes of stars that never had time to live? Perhaps the early universe was not empty, but primed, seeded with unknown processes or hidden physics that accelerated its evolution. Perhaps dark matter interacted with normal matter in ways that triggered rapid star formation. Perhaps primordial black holes catalyzed chemical enrichment by heating and stirring early gas. Perhaps inflation left behind pockets of exotic energy that destabilized gas clouds, pushing them toward complexity. Or perhaps, and this is the most haunting possibility, our understanding of time in the early universe is flawed. Perhaps 300 million years after the Big Bang does not mean what we think it means. Perhaps the fabric of time stretched unevenly, accelerating chemical processes in ways we cannot yet comprehend. The heavy elements JWST found are not just anomalies. They are windows. Windows into a cosmos that behaves like a storyteller, skipping the early chapters and jumping straight into the plot. A universe that prefers richness over purity, depth over simplicity. A universe that wastes no time. And as we stare at these impossible stars, glittering with elements they should not contain, we are forced into the same quiet wonder that has echoed throughout every era of scientific discovery. Why does creation happen faster than physics allows? For a long time, we believe the universe began in simplicity, that it emerged from a singular spark of creation with nothing but hydrogen, helium, and possibility. That complexity was an achievement earned slowly over time. That stars, galaxies, and black holes were milestones in a cosmic journey, from the pure to the intricate, from the quiet to the structured. It was a comforting map, clean, ordered, predictable. A story where simplicity stood at the beginning and everything else unfolded from it like chapters in a well-written book. But JWST has taken our map, turned it sideways, and revealed something unsettling in the margins. Perhaps the universe was never simple. Perhaps complexity was there from the beginning. Perhaps the story we wrote was never the story the cosmos lived. At first, this idea feels like heresy. Everything in science is built on foundations, rules, models, measurements carefully calibrated to avoid wild speculation. But every era of science also has its blind spots, moments when the map outgrows the territory, when the universe refuses to fit into the lines we drew for it. And this may be one of those moments, because if galaxies form too quickly, if black holes grew too fast, if heavy elements appeared before they had time to be forged, then the simplicity of the early universe is not a fact. It's an assumption, and assumptions can crumble. One interpretation is modest. Maybe our cosmology needs minor adjustments. Perhaps stars formed faster in the early universe because of extreme densities. Gas clouds may have collapsed more efficiently, cooling more rapidly, creating a cosmic frenzy of starbirth we never accounted for. If the first stars were more massive and more chaotic, they could have enriched the universe with heavy elements in record time. This explanation feels safe, familiar. It allows us to keep our old rulebook by adding a few amendments in the margins. But even this gentle correction begs a deeper question. Why would the early universe behave so differently? What force or hidden ingredient accelerates structure formation so dramatically? Why does creation seem eager instead of patient? Why does the cosmos rush? A second interpretation goes further. Perhaps dark matter, that invisible substance making up most of the universe's mass, behaved differently in the beginning. Maybe it cooled faster. Maybe it clumped more aggressively. Maybe it created deeper gravitational wells earlier than expected, pulling gas into dense pockets where stars and black holes could form at breakneck speed. If dark matter were more dynamic in the cosmic dawn, everything else would follow. But this too leads us into new mysteries. If dark matter acted differently in the beginning, what changed? Did its properties evolve over time? Was the early universe governed by physics we no longer observe? Then comes a stranger possibility, one that bends not just the rule book, but the book as spine. What if the neutrinos, the ghost-like particles that flow through your body by the trillions every second, had greater mass in the early universe? Heavier neutrinos would alter cosmic expansion. They would affect the formation of structure. They could accelerate the timeline in ways that create the illusion of early maturity. It is speculative, yes, but every explanation now feels like stitching shadows. Each theory hints at a reality where the early universe was anything but simple. And if these explanations stretch thin, we arrive at even more daring ideas. Some physicists propose that cosmic inflation, the violent expansion of space in the universe's first instant, left behind pockets of dense matter, seeds of complexity that primed early galaxies with a head start. Maybe inflation wasn't a uniform. Maybe it imprinted patterns, structures, or even baby universes inside our own. In such a scenario, complexity isn't an accident, it's inheritance. Another group suggests a more profound revision. Perhaps the universe is older than we think. If the cosmic clock we use is slightly off, if expansion rates changed in ways we miscalculated, then the earliest galaxies may not be as impossibly early as they appear. A universe a few 100 million years older would solve the timing problem. But this idea raises its own question. How do you miscount the age of everything? And then there is the most radical idea of all, the one hidden at the frontier of modern cosmology like a quiet, patient storm. Maybe the universe had no true beginning. Maybe the Big Bang wasn't the first page, but simply the latest chapter in a story that extends infinitely in both directions. A cyclic universe, a bouncing universe, a universe that collapses and explodes, endlessly rewriting itself. In such a cosmos, early galaxies may not be early at all. They may be survivors, remnants of a previous cycle, echoes of older universes imprinted into the fabric of this one. It sounds like science fiction. But then again, so did the idea of galaxies too massive to exist before they existed. If the universe is cyclic, then complexity has no beginning. It returns with each cycle, seeded into the next round of creation. Heavy elements could survive. Primordial black holes could reappear. Structures could imprint themselves onto new worlds, creating the illusion of early maturity. In this view, the universe is not a blank slate. It is a palimpsest, the faint writing of previous universes, visible beneath the fresh ink of the new. And if even that is not bold enough, some propose that the universe may not need a beginning at all, that time itself may emerge from deeper, timeless principles, that the Big Bang was not a moment of creation, but a moment of transition, a curtain rising on a stage already built. In this perspective, the rule, the universe starts, simple collapses entirely. There is no start, no simplicity, only an eternal interplay of patterns, fields, and structures flowing into and out of existence. This is not science fantasy. It is what happens when data pushes theories beyond their comfort zones. And this is the emotional core of the act. The shift from fear to liberation. The moment we stop trying to force the universe back into the old rulebook and instead accept a new, humbling truth. Maybe the universe is not breaking the rules. Maybe we wrote the wrong rules. Perhaps simplicity is not the origin of everything. Perhaps complexity is. Look at the universe now, a web of galaxies stretching across billions of light years, interconnected structures shaped by gravity and dark matter, woven with stars, planets, and life. Is it truly so unreasonable to imagine that the seeds of this complexity were planted from the very beginning? That the fabric of space itself carries an inherent tendency toward structure, toward clusters, toward patterns? We assumed simplicity because it felt logical, comfortable, ordered. But comfort is not evidence, and logic is not law. Our assumptions may reveal more about our psychology than about the universe. Perhaps we expected a simple beginning because we understand simplicity, because complexity frightens us, because an early universe woven with structures, patterns, and hidden histories feels overwhelming. But the cosmos does not shape itself around our comfort. It never has. So, we stand at the edge of a map with no borders, no starting point, no certainty. A map written in questions rather than answers. What if the early universe was always dense with structure? What if dark matter sculpted the cosmos from the very beginning? What if black holes were born during inflation? What if the universe is older, deeper, vaster than we ever imagined? What if time itself is not linear at cosmic dawn? What if we live inside a world that is not breaking the rules, but revealing rules we never knew existed? Slowly, something shifts. The confusion becomes clarity. The tension becomes relief. Because a universe that was never simple is not a broken universe, it is an honest one. It is a place where complexity blossoms immediately, where structure emerges as naturally as breath, where creation does not crawl, but leaps. And as this thought settles, the fear dissolves into wonder. Because if the universe was never simple, then everything, every galaxy, every atom, every thought is part of a deeper story. A story that did not begin in silence, but in symphony. Not with emptiness, but with possibility. Maybe the early universe was the wrong. Maybe we were wrong to expect simplicity. Maybe creation starts at full speed and only slows later. Maybe the universe did not grow into complexity, maybe it erupted into it. And as this new perspective unfolds, calm begins to settle over the mystery. Not as answers, but as acceptance. A quiet revelation that lifts the weight of certainty from our minds and replaces it with something more beautiful. Curiosity. Perhaps the universe is not a puzzle to be solved, but a reality to be witnessed. Perhaps the rules were never written. Or perhaps they were written in a language older than physics, older than time, older than the universe we inhabit. And as JWST continues to reveal a cosmos richer than we ever imagined, one truth rises like dawn over the old assumptions. Maybe the universe was never simple. For centuries, we treated the universe as a thing out there, distant and indifferent, unfolding according to rules that cared nothing for the creatures who eventually learned to see it. We imagine space as a silent stage and ourselves as mere spectators in the balcony, watching the cosmic play unfold from afar. But as JWST revealed, galaxies too old for their age, black holes too heavy for their time, and elements too mature for their moment, something quieter began to stir beneath the science, a question not about matter, but about meaning. What if the universe is not indifferent to observation? What if the very act of looking changes what is seen? It's a thought that has haunted physics for nearly a century, ever since quantum mechanics revealed its unsettling truth. At the smallest scales, particles do not behave like objects, but like possibilities. They do not exist in definite states until measured. They reside in clouds of maybe, shimmering with potential, collapsing into facts only when observed. The universe at its foundations seems to wait for a witness. John Wheeler, one of the great physicists of the 20th century, took this idea further. He proposed the participatory universe, a cosmos, in which observers are not passive recipients of information, but active participants in shaping reality. Not creators, but co-authors, not outsiders, but ingredients. According to Wheeler, the universe may not reveal itself completely until minds exist capable of asking the right questions. And now, as JWST peers deeper than any eye before it, unveiling paradoxes hidden since the cosmic dawn, Wheeler's idea returns with strange resonance. Because it feels almost poetic. The universe shows us only what we are ready to understand, as if reality is not fixed, but relational, as if the cosmos is a mirror, reflecting not just stars, but awareness. Imagine that the anomalies JWST reveals are not errors, but invitations, signs that the universe is not a static object, but a conversation evolving with each question we ask. The early galaxies look older than they should. Black holes appear before they could form. Heavy elements glitter where they have no right to exist. Perhaps these contradictions are not contradictions at all. Perhaps they are reminders that our map is incomplete because we have not yet asked the universe to draw the paths we cannot imagine. In this perspective, observation is not an intrusion. It is collaboration. Every time we build a better instrument, from Galileo's telescope to Webb's golden eye reality, gains a new channel through which to express itself. The deeper we look, the deeper the universe responds. It is almost as if consciousness is the universe looking back at itself through biological eyes, rediscovering what it already contains. As if the cosmos and the observer are two halves of a single unfolding phenomenon. For billions of years, the universe expanded in silence. No minds to witness, no questions to provoke answers, no self-awareness. And then, on a small planet orbiting an average star, consciousness blinked into existence. A fragile flicker, a brief awakening. But in that awakening, the universe gained something new, the ability to examine its own structure. We call ourselves observers, but perhaps we are more like mirrors placed inside the cosmic hall. Through us, the universe becomes aware of its own complexity. Through us, the mysteries revealed by JWST acquire meaning. Through us, the impossible becomes visible. And if this is true, if the universe requires observation to reveal itself, then the anomalies may reflect not a broken model, but an evolving conversation. The universe is not defying our rules. It is showing us we need new ones. It is urging us to grow. Perhaps the early universe looks too complex because we are finally capable of understanding complexity. Perhaps the cosmos withheld certain truths until the moment consciousness reached the threshold to receive them. Not out of intention, but out of the deep mathematical resonance between observer and observed. Even the anthropic principle, often misinterpreted, whispers this possibility. It suggests that the universe is observed to have properties that allow observers like us to exist, not because we are special, but because only a universe that supports life will ever be noticed. Consciousness selects the universe by the mere fact of being able to be in it. So what happens when consciousness evolves? What happens when we build instruments so powerful they can peer into the infancy of everything? What happens when minds reach for truths once buried behind billions of years of light? Perhaps reality shifts in response. Perhaps new layers become visible. Perhaps the universe reveals deeper structures because we finally have the language to understand them. It is not that galaxies are changing because we watch. It is that we are entering deeper rooms in the mansion of existence. Rooms that unlock only when we gain the keys of curiosity, technology, and mathematical imagination. And once inside those rooms, the universe feels strangely intimate, elegant, even intentional, though not in a human sense. When stars form too early, when black holes become too massive too soon, when heavy elements glitter at the dawn of time, maybe the cosmos is whispering something profound. That reality is not linear, that creation is not slow, that the unfolding of the universe may be intertwined with the unfolding of awareness itself. For a moment, consider this possibility. Consciousness is not a late arrival in the universe, but a feature woven into its structure from the beginning, a potential waiting to bloom, a sense-making mechanism seeded into matter. In this view, humans are not separate from the universe, but the universe expressing its own capacity to understand. And so, JWST is not just a telescope, it is an evolutionary step, an extension of the universe's ability to observe itself, a mirror placed so far away that when it opens its golden petals, the cosmos catches sight of its own reflection across 13 billion years. Perhaps that is why the earliest galaxies feel older than they should. Perhaps that is why the cosmic dawn looks like a memory. Perhaps that is why every anomaly feels like something familiar, something the universe has been waiting to show. Because in looking outward, we complete a loop. Observer meets observed, question meets answer, matter meets mind, and somewhere in that loop, meaning is born. The universe observing itself, not metaphorically, but literally, through consciousness, through curiosity, through the fragile intelligence of beings who dare to ask why anything exists at all. And as this realization settles, a quiet mystery rises like breath on a cold window. If the universe reveals itself when we are ready, then what hidden truths wait for the next question? In the end, the question that began our journey still echoes softly. Why does JWST keep finding things that break every rule? Why does a telescope, built by fragile hands on a fragile world, peel back the darkness only to reveal impossibilities waiting in the light? Maybe the answer is simpler and deeper than we imagined. Maybe the universe isn't breaking rules at all. Maybe it's revealing them in stages, the way a story reveals its plot only when the reader reaches the right chapter. We expected the cosmos to begin quietly, to grow slowly, to follow the sequence we drew in our textbooks. But perhaps creation doesn't unfold in straight lines. Perhaps it blooms all at once, recursively, like a fractal spiraling outward from a single spark. What if the early galaxies that look too old are simply parts of a pattern we haven't learned to see? What if the black holes that feel too heavy are chapters from a history older than our models allow? What if the elements that appear too early are reminders that the universe has always favored complexity, not simplicity? We call them anomalies, but maybe they are invitations, doorways into deeper layers of reality, waiting quietly for us to notice. Because the universe began as a paradox, everything exploding from nothing, time awakening from silence, order rising from chaos. Why should its oldest pages be any less mysterious? Why should its earliest structures obey expectations crafted by minds that arrive billions of years later? Perhaps the universe does not owe us simplicity. Perhaps it never wore the clean, predictable symmetry we once imagined. Perhaps the rules we cling to are only reflections of our current understanding. And as JWST continues to search the darkness, revealing a cosmos that grows stranger, richer, and more intricate with every glimpse, a final thought settles over the journey like starlight on quiet water. Maybe the universe was never meant to follow the rules written by minds living inside it.